So welcome back. Before we went on break, we had a review at what we did the other time, and we took a very quick run through to MongoDB and the Spark integration, and the most important thing is how we remodeled the database. Now, remodeling does not necessarily mean you have to be doing big data. You can literally remodel an OLTP system based on a relational data model to a NoSQL system like Cassandra. So what is Cassandra? Excuse me. So Cassandra is a NoSQL wide columnar store database that is used to store data that require fast writes and a very considerable amount of rings. A considerably quick response for reads. So it's a project that started at Facebook and was used to solve email problem. And you will see some very, very important things about Cassandra that we're going to take a look shortly. However, in line with the tradition we did in the other session, I would like to refer you back to the dbengines.com website where we have over 180 databases that are ranked both according to their popularity universally and according to their popularity in their various classes of database types. So if you look at this, you would see that MongoDB is the fifth most popular database out there, and also the most popular document oriented database, right? And also from the list, you can see right here that Cassandra is the 11th most popular database and the most popular wide columnar store database. So it's a big deal that we're learning or using this kind of technology. We're basically on the front line. If you go into, you see it's a wide columnar store that was based on the idea of Google Bigtable and also highly influenced by Amazon DynamoDB paper and database. So, like I said, columnar database that favors availability over consistency, but I'm going to touch more on what that really means. But it doesn't have a single point of failure. So remember when I told you about MongoDB? Let's take this for instance. Let's say we have a database. We say we've got a database right here. We have another database right here. This is a Mongo. Let's say this from a MongoDB cluster. And for the sake, let's say this is the network hub. So they're all related. Now this could be the master, and this is slave 1 and this is slave 2. So remember, in a master-slave relationship, you had a single point of failure because for whatever reason, if the master goes down, we are currently or totally unavailable. So for instance, let's say this guy goes down for the time being. So these databases have the ability to elect a new master, but for the time being that we are making a decision who should be the next master of S1 and S2, for that time being, the relational database is not going to be available. And also in different hacker days, we've used a lot of HBase, and we've also seen it's a master. It also uses the master-slave architecture where we have a H master and we have region servers, which we will now call the slaves. So in the same way, in MongoDB, we have master-slave. However, when we come to Cassandra, Cassandra has no single point of failure. How? Because it uses this kind of ring architecture. So let's do a 4-node Cassandra cluster, right? So this is 4 nodes, and let's say in the middle we have this small box that connects them together. So these are the nodes. So this is one way we can draw them, but in most Cassandra textbooks, this is what you're going to find. You're going to see this kind of representation. You're going to see something like this. They're going to tell you it's a ring architecture. So I am trying to be a little more physical than logical. So why I like using this one, why I like using the network, I like using this one. I mean, this one over this is because in this second one, it appears that this server is only talking, A is only talking to C and B, right? So it appears like A is only talking to C and B, but in actual fact, A is talking to every B, C, and D. D is talking to A, B, C. B is talking to A, C, D, and C is talking to A, B, D. So they all talk to each other. So that is why in my own mental representation, I prefer to use this one over this. So no single point of failure, meaning that it is a peer-to-peer system, right? So they use is like a peer-to-peer architecture. So and there is no master. If one node goes down, literally the data available there will not be ready for read. However, because of the concept of replication factors, we know that copies of the data that's in a node A will also be around in some other nodes B and C, D, right? So if that node goes down, everybody keeps working, right? And that if there's no master and there's no master-slave relationship, it means that any node can serve your query. So if you can connect to one node, you're just as good. You're just as good as you're connected to the whole cluster. So if you connect to a node, that node will be what we call the coordinator node. So that node will coordinate your query. Even if the data you're looking for is not in that node, guaranteed that node will be able to kind of answer the query by directing the fetch of data to the appropriate node. So what we normally call this in Cassandra is called the ring, right? So that is why you always see that in textbooks, you see that diagram where they show all the nodes as in a circle, right? But like I said, I prefer putting things like this. So this is a ring. So let's assume that I am right here and sorry. So just assume that I am right here, right? And I am connected to D, right? So I can do my read there. I can do my write from D. However, let's talk some very cool features of Cassandra. If I make a write request to D, D is able to take the data, look at my primary key, and look at my partition key, and it will determine which of A, B, C, D should this data leave primarily. So which of them should contain the data as well as the replicas. It makes that decision and sends the data there. In the same way, if I want to read data, I will issue a query to D, and D will take that query and also giving where clauses or whatever I request, is going to make a decision which servers A, B, C, D is containing the data. So this is one way where any node can serve it. Now, the best case scenario is that the data is in D. So it will serve me locally. It doesn't have to go out. It's just going to fetch me that data and it returns it. And the worst case scenario is that the data is in another server, probably H in a continent away, right? So you have the server in Asia, but you're making the query from North Africa. So that is the worst case scenario. It's still going to fetch it, right? So also, if it's not able to reach, it's also able to make the decision that the data is primarily in a server in Asia, but there is a replica of that data in another server in another country in North Africa. In that case, it's going to make the query from the server. It's going to do that proximity preference by picking the data from the closest server, right? So how do these guys know about themselves? If there is no master, how do all these nodes know about themselves? They actually use what we call the gossip protocol. The gossip protocol. So the name tells you what it is. Each node talk to themselves like they send a heartbeat of themselves and they get to say I'm alive. So every node knows kind of I made exchange to all the nodes that I have on my list. So I know the node, I have a journal of nodes that are alive. That is one. They also make use of what we call snitches. So with snitches, including gossip protocol, I'm able to tell which of the servers are closer to me than the other. So that's how I'm going to decide that I should query the server that's in the next country, North Africa, and not the server that is in Asia. Because as they snitch among themselves, they're able to calculate, it's able to determine who is closer and who is in another data center, another country, or another continent altogether. So no single point of failure, availability and flexible consistency. So if we go back to the CAP theorem, where we drew something like this, we say this is consistency, this is availability, and this is partition tolerance. I don't know in what order we put them. This is where Cassandra is. So Cassandra is right here. MongoDB was right here. So this is Cassandra. So, but the truth is Cassandra actually offers, Cassandra did not totally sacrifice consistency. It actually offers what I call flexible consistency level. So Cassandra can determine to be strongly consistent, and in that very academic sense, come here. Come here. And in that way, it will give up availability, right? Because for some reason, some nodes will go down. And for some reason, you can get technical errors trying to connect to some nodes. So it can also choose very loose flexibility, very loose consistency. And in that case, it will give preeminence to availability. So you hear people say it is AP, but just like MongoDB, I will want us to say, I also say it is AP as well. So I'm not saying people say, I say it is AP, but we should also know that in practice, it literally shifts along the line. It can be CP if you configure it, or if you configure your use of Cassandra to be AP, to be CP. Now, another thing to note is that this configuration I'm talking about is not some configuration file. It's just the way you connect to it. And so you can say, you can connect by saying the write consistency level, the read consistency level. So it's all in your query. It's all in your connectivity to Cassandra. It's not in some config file of Cassandra. So what have we said? Cassandra is a wide columnar store. It can handle thousands and millions of rows, of records. It can handle millions of rows, right? Good. So now we understand the architecture, the ring architecture, no single point of failure. Everybody in the node can be a coordinator node, so you can connect to them. So if you are in Nigeria, and there is a data center in Nigeria, it will make sense for you to connect to that one. It's going to serve you. And if your colleague is in Egypt and there's a data center in Egypt, in North Africa, he can connect to the server in Egypt. If you have another data server in, say, Sri Lanka, and there's a guy who is in Sri Lanka, he can connect to any one of them, right? They will very well serve. Okay, having said that, let's talk about why it is called a wide columnar database. So when people say that a database is columnar, the first thing I like to think is that just like when we say a packet is a columnar structure, it's like the data is stored in columns. So my name, my age, my gender, and my location. I mean, this is what we think that a columnar structure is. So right, we do this, right? Then the instance of the date, and this is ID. So 1 Michael, 25, male, Johannesburg. That is what we think as columnar data structure, right? But I'm going to tell you why it is exactly not the way to think of wide columnar structures, even though you still see some databases that store data like this. So let me talk about it in the sense, because I've also talked about a lot of HBase in a lot of hacker days. So I don't want to use relativity to HBase, but I want you to get this right. So when we call wide columnar structure, it's simply because number one, it is schemaless, not because the way the record is arranged. It is because it is schemaless. And that means that rows don't share column. Rows don't share columns. So that is what you want to think of as a column-oriented database. It means rows don't share columns. Remember, in Excel or in a relational databases, rows share columns. So let's explain. Once we put data like this, and once we have said this is ID, this is name, this is age, and this is location, all rows will use this column, right? They will share column. But in columnar databases, just like HBase, they don't share columns. They are not tables per se, right? They don't, it's not a strictly two-dimensional structure where all the instances along a vertical axis have the same data type and the same property. No, that is what we literally mean by columnar store. And what this means that internally, right, you can have a row that has columns, 5 columns, and the next instance of that record will have 20 columns that don't intersect with the columns above. Perfect. And this is because of the way records are stored. You want to think about it as that big hash map. As a matter of fact, before Cassandra 3.0, what I used to know, because I took a while off Cassandra, so I was one of the most confused people between Cassandra 2.0 and Cassandra 3.0, right? Why was I confused? Because of the major changes that happened in Cassandra 3.0. So previously, when I was a bigger Cassandra fan, it was a thrift interface and everything was a hash map, was a gigantic hash map, just like HBase, right? You remember HBase? You put a row key and then you point to a column family. In fact, it used to be called column family, not tables, but now it's called tables. So like I said, I was one of the most perplexed people. Say having this out of body experience was like, I know like 2 years ago I used Cassandra, so what has happened now? I don't know anything in Cassandra. Yeah, because there was a change and they brought in the concept of CQL, but I'm going to go there. So let's talk about how it used to look like. So you have a row and you have a column family, and remember the word column family means bunch of columns, and these columns are stored. Now this row is literally called the primary key, right? And records are stored sorted by primary key, right? They are stored sorted by primary key. So it's very easy to do range query because you just know where the data is and you can go on from there. So data are stored by primary key. And when you come in here, columns are stored. Column name is key value, column name and column value, right? And there is an inside timestamp that comes with this data. So you want to remember HBase. For those of you who are familiar with HBase, it looks like that. DynamoDB, yeah, something like this. I'm not a user of Dynamo, by the way, disclaimer. So you have the role and you have a family of columns, and inside this family of columns, you now have, I don't want to use the word cell, but just think about it like key value pair, where the column name is the name and the value is the value for that cell. So if you take this key, you can look up this entire row. Remember, the next row can decide not to share any column name, can have its own different type. It made it so schemaless and it made it super flexible until 3.0, when I figured out that I had been away for a while. So let me explain, and this is what happened. So the reason made sense. The reason is because they wanted to put more structure to expand the use cases of Cassandra. And I totally agree. When I saw the reason, I totally agreed. but it makes it look like we are now doing tables, right? But it still makes it important for you to know that the internal way the data is stored has not changed, but the way we now deal with the table has changed. So it looks like we are using a relational paradigm to discuss Cassandra that was supposed to be a schemaless database. So now let's talk about the data models in Cassandra. The biggest I will say will be the key space. So like key space is another word for the container of all objects that will live within one namespace. So think about it like a database, right? Think about it like a database. So if you go to a MongoDB like we did last time, we call it a database as well. So under the key space, we then have tables. So like I said, it used to be called column families, but since 3.0 and the advent of SQL, Cassandra Query Language, we now call them tables, right? So tables are tables. You now create the table, and when you create the table, you specify the big deals in the table. So a table will contain a primary key. So this is the lookup. This is the row key. This is the guy that helps you with that speedy lookup. And remember, I told you about the ring architecture. So the primary key doesn't just help you with fast lookup. No, the primary key actually also tells you which node in the cluster that the record is. So it's not just one fast lookup thing. No, it tells you which node in the entire cluster that lookup is. So when you submit your query, let's say select star by this and by a primary key, Cassandra will use what we call a partitioner to derive a token from that lookup value. So it will use a partitioner it will pass in a function, and using on that row key, it will get a hash, or what we call a token. It will now know which node has that token. So every node has a journal of which node has a range of tokens, right? So so let's talk about rings and tokens. So ring is only one, and token. So ring is that stuff I drew for you, the network, right? That you have node here, node here, node here, and node here, right? So just assume this is the ring. And so if I submit a query with a primary key, you figure that I need that primary key, it is going to get a token, and that token is going to say, let's say this guy is token 1 to 50, 51 to 100. This is 100 and 1 to 150, and 150 to 200. So let's say the hash function produced a token value of 65. Right, so which node has 65? Would say it is node. Sorry, just want to change the color. Okay, cool. So which node has 65? Is A, B, C, D. We said node C has 65, so that request hits node 65. Fetch me this value. End of story. So that is why, and that is how it addresses which record is in which node using the token, right? So you can see the purpose of the primary key is not just for simple fast lookup, but also for location. So a primary key can consist of a partition key, right? And also clustering keys. So let's talk about this very quickly so that when you hear someone talk about these things, you already know them. So in each node, records are kept in like partitions, right? And a partition is identified by a partition key, right? So clustering keys determine how the records are ordered. So within a partition, let's give an instance. So we can have like okay, let's take a test case. So we have MOT data set, and a vehicle could go for testing many times, right? If we choose to use the vehicle ID or the registration number as the primary key, that's a problem. And I'll tell you, the problem is because if you do another testing, you overwrite the data. But let's say we decide to use a composite key. We decide to use, we decided in the primary key, we decide to use the vehicle registration number or the vehicle ID as the partition key and the test ID as the clustering key. So we're going to have these two as the primary key. One, vehicle ID, it tells you where the data is. Then the other is the test ID. So first test, second test, third test, within that partition, they are going to be ordered. Right? So a table, primary key, clustering key. A primary key contains the partition key and the clustering key. The clustering key tells you how records will be ordered. Okay, so we've talked of key spaces, tables, ring. You can also create indexes. We call them secondary index because primary key is index enough, right? So it just helps you with faster lookup. So you can create indexes. And something else I will reserve for later, and that will be materialized view. Materialized views. Right, so that's another thing to talk about. So now that we've seen key spaces, tables, primary key, then we have static columns as well. So static columns are columns that, even though they are shared by all the rows, right? So you can have a static columns. Static columns are columns that are shared by all the rows. Okay, so we've talked about replication. Replication is not master-slave, it's peer-to-peer. And we can confirm these. You can look up more properties. A second. Okay, good. It's working now. So you can look up replication. So it uses replication factor. And we have immediate and eventual consistency. Like I said, very flexible consistency mode. Okay, the big deals. We don't have foreign keys. So there's no relationship between tables. We don't, and as such, we don't have joins. You cannot implement joins. Doesn't work. Right? What else don't we have? So once you don't have, and the most important of all, remember, you cannot create foreign keys. You cannot have joins in your query, not supported. But the most important you don't have is you don't have the ability to change the model of your database once you have created it. I repeat, you don't have foreign keys, you don't have joins, right? And the most important don't have is you don't have you cannot change the structure of a table or the model. No, not the structure, because that you can change the structure using an alter table, but you cannot change the model property once you have created it. So it looks like I am contradictory. So let me take it slow. So it's schemaless. So I literally can add another row, right? But I cannot do something like I create a table, right? Then I want to alter the table to add a new column to the primary key. I can do that. I can, however, create a new table that looks like that and copy data from one to the other, right? So that is one of the most restrictive features of Cassandra that I know, right? Even secondary index, restricted, you can see that. So one of the most features I will repeat is you cannot change the model, the primary features of your model once you have created it. Instead, you create a new model and ship data from one place to the other. That makes the biggest work of modeling data in Cassandra conceptual at the conceptual stage. The biggest job is at the conceptual stage. Now remember, in MongoDB, I literally can create a mod. I just jump, I create a collection, and like I figured out that I needed outcome.result as an index. I can go bam, 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 create index on this table, then I query it. Not with Cassandra, right? You can create an index later, but it is restricted, and you will begin to have issues with it. Number one. Number two is that if the index you're trying to create, you want it at the primary level, then forget it. You cannot have it. That is why to learn Cassandra, the biggest thing to learn is modeling. So is this enough to chase you? No. So yeah, it's somehow a no-brainer for me. For example, this is a typical example. Let's just relax on this. I'm doing a job for a client, yes, still ongoing, and we're supposed to create a very wide table. The current design of that table stands at 1,600, 1,400, between 1,400 and 1,600 columns. And we're trying to model this data to take care of indexes. And so we tried using HBase, and because the client wants to use SQL, we modeled Phoenix over HBase. Felt too slow. We tried others, and one reason why I'm telling this story is because of Cassandra. Is that we were trying to use which solution we're going to use, given that the client was not really cool with Phoenix over HBase, right? So it wasn't cool. Now, one reason why we could not do Cassandra is because we still did not know how the client was going to use the data. So we settled for another solution, a cloud-based solution, and that can allow arbitrary coding. However, the solutions still have that restriction, but because it is very arbitrary, we can live with it, right? The import of what I'm saying, I meant to tell the story to say that with Cassandra, you have to model your data to your query. You have to model your data structure to your query. Modeling is to favor read, not to favor write. Right? When we modeled the data in MongoDB, we modeled it from a very, very logical and functional standpoint, because we wanted to say that a test record has a test item or not. So we consider that test item a property of the test record of the test result. So if the test result is pass, then it has no test item. But if it's failed, then it has one or more test items. So we made that an array of test items, right? And it makes very, very logical sense. You can actually draw this on the blackboard, right? But you can see we modeled it from the business and considered it as a document. And from that, we created a MongoDB document. However, I can't do that in Cassandra. For me to be able to model it, the first question I will ask you is, how do we want to query the data? How do we want to query the data? Because that determines what is going to be my primary key. And you know, the most important thing about the primary key is which node is going to be stored. So bottom line, you need to know how you're going to use the data to be able to model the data. It's something I don't like, but I have become used to it. For instance, we do that same thing in HBase. You cannot model data if you don't know how you're going to use the query when writing HBase. And come to think of it, you do it also in Redis. You cannot model the data as key values if you don't know how you're going to use it. So what's going to be the key? Right. So if you're going to use it in many ways, sometimes it means you have to duplicate data. And yes, in databases like this, you might have to duplicate data. And Cassandra can accept that as a trade-off, because writes are blazingly fast. So we shift a lot. We are always so biased to preference of read performance because of what Cassandra always gives us in write performance. So before I now jump, haven't talked about these things, you might sound a little depressed. Why would somebody use Cassandra then, right? So what are the use cases for Cassandra? The first one I will tell you is for web scale data. And if it turns out, you would see that what we're doing, our use case is web scale data, at least in our context, right? So I said the data set for 2005 alone is how many? 7.4 million, right? If you click on this show more, you see we have between 2005, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, if you imagine you're having this kind of data coming into your business or your enterprise every day or every month, you are within that neighborhood of web scale of very large data set. You're within that neighborhood of operating a big data at a transactional level. So let's put it this way. You use Cassandra when you have web scale data at a transaction level. And because it has very good rights, it is also very good for our Internet of Things. So you can actually put in hundreds of thousands of writes per second. Right? It's going to scale very well because of the rights. So also good for transactional application in the web scale. Remember, you can make it to be you can really alter the concurrency level, and you have availability. You can also you have replication, so the data are replicated across the ring, right? And if one node goes down, if one node goes down, we pull it out, we push it back in, configure it. It just gets to know itself, and it's assigned its own token range, and it starts receiving data. Right? You don't need to shut everything down. You don't need to elect a new master. It just blends in and continues. Right? If you want to perform some setting operations, for example, you cannot have issues like skewed data where only one node is writing and the whole guys. If you design your model well, you can literally design to throw away that kind of skewed data operation. Also, Cassandra integrates very nicely with big data platforms. As a matter of fact, you can use Cassandra also using some setting design patterns as a graph database, as a search database, and with the help of the Hadoop stack, you can use it for analytics. So, analytics sounds like we're just trying to analyze data across many segments, many dimensions. And now it looks like you cannot just do that because you don't have join. You can only use certain keys for your where clauses. So can I use it for analytics? Yeah, the big place where Cassandra plays analytics is when you're using it with the Hadoop stack. For example, using it with Spark. Right. But when you come to very high velocity systems, or for instance, when you're dealing with high data streams, Cassandra is one of the best guys in that space, right? For example, if you've heard of this stack, SMARC, right? Where this is for Spark, this is for Mesos, this is for Akka. So the Scala framework, this is our Cassandra, and this is for Kafka. So there is this popular SMARC stack, and it is something you just want to look up. All you have to do is just say SMARC, and you want to add big data because I'll smack you could be a word. So SMARC stack, right? And people ask, is it a hype for big data or what we're using it for? Now, the reason I'm saying this is because you can see that it's something that can handle that kind of very fast writes. For example, you're handling trading data from a live trading feed, and you're doing it for hundreds or even thousands of currency or instruments, for trading instruments, and you are getting ticks, probably 3, 4, 5 ticks for each per second. And so across board, you're probably writing in 20,000 records per second. And you're not only writing them, you're performing real-time calculations, you're running you're running quantitative calculations on the flights of this data, producing real-time trading indicators and alerts. Now we are in the zone. We are in the Cassandra zone, right? Because the read models for this kind of system are very simple. It's the same thing with HBase, right? The read models for this kind of system is very simple. We're writing in data as fast, and we read them based on a very simple model. Probably writing trading data, you're looking it up by the currency pair and the date. And the data is range. So it's very easy to do very quick reads because of the way the data is stored within partitions. Right? So these are where it shines. But are you going to use it for an application that we don't know how we're going to use it yet? No, please don't. You want to probably go back to MySQL and use it over a period, and when you get those pain points, you would know how to upgrade to a different to a NoSQL system. So that is Cassandra in a nutshell. The use cases, Internet of Things, you can use them in a graph context, you can use them in a search context. Internet of Things, streaming data, very good for that. Remember, no point of failure, always available, even when about half of the cluster is down. Also, it's a good place. Cassandra has its very use if for multinational companies. Let's pick a big multinational company like ExxonMobil, right? So these oil conglomerates, right? So they could have data centers across the world. How about have a unified data center where anybody around the world can use the data? So we have data in the US, we have a data center in the US, we have a data center in Asia, we have a data center in Nigeria, we have a data center in Chile, right? So these because of the way replication occurs, right? Because of the way replication occurs, and replications, read and write queries in Cassandra can be rack aware, can be data center aware. So you can configure it to say, so let's say replication factor of 3, write 1 in this local data, in this rack, in another, in this data center, and write 1 in another data center elsewhere. And that data center could be, you're writing from Chile and it is storing the data in New York, for instance. So, and that means if something really bad happens to Chile, right? The Chile data center, right? There is an earthquake or fire or something, right? We have still not lost data because we can just bring up some nodes again in another location, and the data in New York replicates back, and we literally lost nothing. Cool. So it is good to like keep data across very wide for a very large enterprise like that. Nothing is lost. Remember, everything you've lost with ability to do arbitrary queries, analysis, implement complex UDFs and data munching, once you integrate Cassandra with Spark, you gain everything back. As a matter of fact, Cassandra with Hive, you get it all. So I can literally query from Spark arbitrarily, right? Cool. And that is what we're doing. So we've got a use case. Excuse me. So we've got a use case, and this use case allows us to be able to read data very fast and write data. So let me explain fast read or fast write and read. So I am going to, not very comprehensively, but I'm just going to lay down how read and write happens in Cassandra, right? So let's start from this. So if we have, let's do write. So this is me, like I'm right here, sorry, right? And for instance, let me say this is the ring. So they are connected by an invisible network right now. So let's say I connect this guy and I write data. So when I write, I'll supply the primary key. So with the primary key, this guy is now my coordinator node. Is the coordinator node, is the connecting, and you can have, you connecting to the same cluster can be connected to another coordinator node. They all will serve as coordinator nodes. So when I supply the primary key, it's going to apply the partitioner, and the default is Momo partitioner. That Momo partitioner with the it can generate tokens from like 2 to the, yes, some very large number, 2 to the, I think, 63, 2 plus 2 to the 63, something like that. So very large number. I mean, literally unlimited in a human context. So it's going to calculate a value, and that value will be a token. Now that token will now decide which of these nodes, right? So there's a concept of virtual nodes, but let's leave it at which of these nodes will handle my data and the replicas. Now, the replication strategy is determined by what we call the topology of the, it's also by the topology of the cluster, right? So for example, you can determine that the replication should be rack aware, should be data center aware, or a simple just drop 3 things near the old guy. And it is pluggable. Literally, you can apply, you can create your own if you don't like it, right? So let's assume after getting that, we figured that it needs to write it to 2 places. So it will write one here, it will write one here, and it's going to write one here. So here. So in this case, it's local. So it's going to store it locally. So we have 1 copy here, 1 copy here, 1 copy here. This is based on replication factor of 3. So when will Cassandra acknowledge that the write is complete? That's the question. When will it gonna acknowledge that the write is complete? It's going to acknowledge it based on the consistency level. Now you can have consistency level of any. So once if you use consistent level of any, once this local one is complete, it's done. It just comes back, right? It says it's done. Did these 3 complete? We literally don't care. They can complete at your own time. Also, you can say complete write consistency level of 2. It's going to write here and write here, right? If you say consistency level of 3 of quorum, it means n over 2 plus 1, where n is the number of replication factor. So if 3, then it's just write in 2 and come back. If you say you want all consistency level, so all should be done, then that is strong consistency, because then we need this to write, this to write, and this to write. And should any of these fail, the user is going to get a write failure exception. So something happened while the write was happening. And that is where we get strong consistency and break availability. You understand that now? So you should use these to understand the use cases for Cassandra. So also, when we read, so let's look at a read scenario, high-level read scenario. When we read, so we say select star from a table where we pass in the primary key. So this is me now, and this is still the ring connected by an invisible network, right? It's connected by an invisible network. If I submit the read request, so just assume that I submit the read request, it's going to use the primary key to determine You can excuse me for a while. So let's talk about a read. So this is talking about a read. So this is like me standing here. I write a query and I read and make a read and I supply the partition key. And when I supply the partition key, once again, this node becomes my coordinate node. It literally could be any node, but this, let's as I take this node, is my coordinator node. It takes the partition key. Let's say we'll come to, let's just try to make things a little bit different here. Let's say for this, we had A, B, D, and C. So when we come to this other case, let's assume this is D, C, A, B, right? So now I make a read, I connect to D, but it turns out that D already contains a partition. So when it uses I supply the primary key, it looks at the primary key, say, okay, pass it through the hash function, gets the token, and figured out that the data is right here, right? It's going to pick the data up. However, it's also going to send a read to C and B, right? And what it does, and when it does return the result, depends on the read consistency level. Remember, it could be that all these three replicas have not yet been in sync, right? So let's assume it does a read and a consistency level of any, it's not good because then it's just going to read, you're going to get dirty reads. But let's say we have a very strong consistency level. It's going to pick up D, then it's going to ask the others to return their results. So it's going to get a result from C or B, then it's going to look at a timestamp. If they are consistent, so if they have the same hash, so the checksum value are the same, that means they're all the same. It picks two and it returns the request. However, if one has a lower timestamp, then it will do a read repair, right? Kind of like fix yourself, update yourself because you are behind the other guys. So you can see that it does that synchronization during a read. And not just because of that, the read and the write path kind of differ. So the write path goes through a shorter route and the read path goes through a longer route. That is why read takes more time and write takes shorter time, faster writes. And that is why when you design with that bias to make sure you design for reads. So we're going to end this right here. Take once again another short break. When we come back, we'll go into installing Cassandra. We'll install Cassandra and we conclude the next session with the read and the write path, the details within the read and the write path. So let's take a 5 minutes break and we return shortly.